Okay. So our objectives, we're going to learn about the self-ionization of water, and we're going to learn about Kw, the constant, the equilibrium constant for water. And then we're going to talk about the relationship between pH and hydronium ion concentration. And then we're going to learn 4 different little things here that will connect to each other that will help us calculate concentrations of hydronium and hydroxide ion concentrations and our pH and something called pOH, which you might not have heard of before. So walking out here today, you're going to write an equation representing self-ionization of water. And then if I give you one of those values there, you should be able to get the other 3 values. All right, so we're dealing with aqueous solutions. And of course, this aqueous solution is going to involve water. And this is called the self-ionization of water. This is what happens all the time in water as it just sits there. You're looking at a glass of water, and this is happening at an incredible rate continually. Okay, we take one water molecule, and that one water molecule decides it's going to give away one of its hydrogens, and so it gives away that hydrogen to another water molecule. That water molecule now becomes an H3O plus, and then it lost its hydrogen, so it becomes an OH minus. So every 2 water molecules that you have in some water, one of them is going to give away a hydrogen to another one, and one of them is going to become H3O plus, another one's going to become OH minus. This is self-ionization. Remember that ionization is the process of taking a molecular compound and turning it into an ion. And that's what's happening here, right? 2 molecular compounds, the water, boom, boom, and that's turning into 2 different ions. And this is happening at a rate where every single water molecule that you have is going to be transformed. And again, you'll notice that this is a equilibrium reaction. So this is happening in both directions. You're going to have some of these ions turning back into water again. And so this is what we call self-ionization of water, and this is the formula for it. H2O as a liquid plus H2O as a liquid is going to turn into H3O plus aqueous plus OH minus aqueous. Now, what we've done by experimentation is figured out how often this happens, okay? We learned yesterday that amphoteric means that it can act as an acid or a base. And because one of the water molecules is giving away a hydrogen and the other water molecule is receiving the hydrogen, that means one of these water molecules is an acid and the other molecule is a base. So it is being both. And what we have done is we have measured this. Because it's a very weak electrolyte, we can measure the amount of this process that is taking place. And so we figured out at 25 degrees Celsius that the hydronium ion concentration and hydroxide ion concentration, because it has to happen in an equal amount, right, is going to be 1 times 10 to the negative 7th molar, okay? And so if I want to figure out my Kw, remember we learned a couple different Ks already. We learned the Ksp, we learned the Keq. This is our Kw. This is what the equilibrium ratio, that concentration is, right? That equilibrium ratio of their concentrations. And we can see that it's going to be the hydronium ion concentration times the hydroxide ion concentration. And if they're both 1.0 times 10 to the negative 7th molar, that means that we have our value at 25 degrees Celsius of 1.00 times 10 to the negative 14th. Remember, there are no units on K. And so we get this value here being our K value for water, just pure water. Now, how many of you guys, by a show of hands, would say that 1.0 times 10 to the negative 7th molar hydronium ion concentration is a small amount? Raise your hands. How many of you would say this is a large amount? Okay. So, thank you for being courageous and actually raising your hands. Most of you said that this was a small amount. But I want you to pay very close attention to the unit here. What does that big M stand for? Moles, right? Moles per liter. And so a mole is a huge amount, right? 6.022 times 10 to the 23rd. And so if I have a fraction, 1.0 times 10 to the negative 7th of 6.022 times 10 to the 23rd, then I'm basically just going to be subtracting 7 from 23. So while you might think of 1.0 times 10 to the negative 7th as a small number, It is not a small number when you are saying it's just a fraction of a gigantic number. We are still talking about 16 zeros, basically, right? 16 digits past the 1. We are talking about something that's huge. And so, is it huge for us in terms of numerically what we think of when we count? Yes. Is it huge compared to a mole? No. It's really small compared to a mole because a mole is so gigantic. But this is still a gigantic number to us because what are we talking about? 16 zeros, right? You're talking about going into what, the quadrillions or something like that, right? So we have still got a ton of particles that are doing this exchange continually. They're going back and forth and exchanging these little particles over and over and over again in a glass of water that just sits there. Okay, that would be in a liter. How much is that in terms of actual volume? Not much at all, right? Because if you think about it, if I take a liter and I take and factor it down by 10, I've got 100 milliliters. I factor it down by 10, I've got 10 milliliters. I factor it down by 10, I've got 1 milliliter. I've just done that, was that 3 times? How many more times do I have to do that? So we're talking about, even though it's this gigantic number like quadrillions, it's in such a small little space you wouldn't even be able to see it with your naked eye. That's how huge it is, and yet how small it is at the same time, because a mole is gigantic. And remember, a mole is 6.22 times 10 to the 23rd, in this case, molar per liter. And so you're talking about a liter of volume. And so this is going to be quite a fascinating thing to think about. All right, so we have this K value, and this K value is something that we're going to tie to our pH. Okay, so let's see how we do that. Does anybody have any questions so far? Okay, so if we have an equal amount of hydronium and hydroxide ions, we have something that's a neutral solution. If we have more hydroniums than hydroxides, then we have hydrogens to donate, right? And we just learned that hydrogens being donated is what an acid is all about. And so we have an acid if we have some hydronium ions to donate. If we have more hydroxides than we have hydroniums, then we have more things that can take on some of these hydrogens. And so we have a base, because overall the solution is going to be accepting of protons compared to donating of protons. Okay, so if hydronium ion concentration is greater than hydroxide, you have an acid. If your hydroxide ion concentration is greater than hydronium's, you have a base. Okay. If they're the same, then they are neutral. Okay. So let's look at how we would solve a problem. This is basically a GEMS problem, right? We have a formula that we've learned. Okay. We have givens. What is the hydroxide ion concentration in a 3.00 times 10 to the negative 5th molar solution of hydronium ions? Okay, so what is our givens? We have hydroxide, and you just write it out like this. Hydroxide ion concentration equals question mark molarity. Hydronium concentration equals 3.00 times 10 to the negative 5th molar. And then what is the other value that we're looking for that we know because we memorized it already? Kw. So Kw equals 1.00 times 10 to the negative 14th. No unit on that. Now we can take our values and we can plug them in to a formula after we rearrange the formula. Notice we rearranged our formula here to solve for hydroxide. And so hydroxide is the Kw divided by hydronium ion concentration. And so then we take those values. This could have an M on it, right? But this one doesn't have a unit. And so then we get our answer of 3.33 times 10 to the negative 10th molar. Okay. Now, we practiced some of this in the last class period. And I will tell you that we had way more incorrect answers than I expected, especially considering that everybody had the right work. Guess what the problem was? You guys have got to still remember how to use these calculators for the exponents, because you have to use these calculators for this test. So we're going to practice some of these now. And if you are not really sure you know how to use these calculators, I would come over and grab your calculator so that you can get ready for doing this on the test. And the problem you're going to try to solve is this one. A solution contains 0.0045 molar hydronium ions. What is the concentration of hydroxide? If you're having trouble finding, you can use the numbers here too. So like Maddie's 19. How do you get the what? So it's the little second and then EE. No, nope, you just do this and then you go second and then EE. And then put in the 14. And then make sure you use that number for the, or that value for the negative instead of the minus. Remember that you want to use this little minus sign down here for your negative value, not the one that's the operation, okay? So don't use the operation when you're trying to do negative 14th. Use this little guy down here. And remember, it's second EE, and then the value, don't do a times in there. Good.
I think we're just. Are we supposed to solve something?
Yeah, you should be solving for this new problem right here.
Oh, I just did the 1.01. Okay, shoot. And you did this.
I got a syntax error.
Let's try it again. Why don't you show me what you did? Okay, we don't want to do the times. We just want to do 1 and then second EE. So second EE.
How come?
It's just the way these calculators work. And then you do a 14 and then put a negative sign on it. Oh, I guess I should have done the other way around. Negative and then 14. All right, now you can do your operation. Divided by.
I get the same thing if I did 1 times?
What I find is that students get the wrong answer when they try to do the multiply, and they get the right answer when they do it this way. So it's kind of the same thing, but it's not the same thing in terms of how the calculator works. Ooh, should have been to the 12th. I'm guessing you use the multiply sign in there somewhere instead of, yeah, you see how you used that times 10? You basically multiplied it by 10 and then you did it times 10 again. And so you've got the wrong answer because of that. No. Yeah, you did a multiply and then you did the 10. We want to make sure that we're using the second EE button, second EE, to do these calculations. So it should just basically be 1, second EE, and then 14 with a negative. Don't forget there should be a negative too.
Can we just use this little button up and then do 10 to the negative 14?
This button does work, and you got the right answer. So if you did you use the second EE or did you use that button?
I use this little arrow.
Then you're okay. A lot of people will mess it up when they use that button, so that's why we mess it up. I don't know, but I get a lot of kids that get the answer wrong when they use that one compared to when they use this one. Yeah. All right, so on this one you should have had the same work that we just showed you, right? But we just had a different number in there, right? We would have had this 4.5 times 10 to the negative third number that we would have divided by instead of the 3.00 times 10 to the negative fifth. If you plug all that value in, you should have got an answer of 2.2 times 10 to the negative 12th molar. If you did not get that, that means you are still using your calculator just a little bit incorrectly, and I need to come around and help you. Anybody need some help?
So 1.00 and then what?
And then just go second EE, and then just do the negative, and then 14. And now divided by, there you go.
5.
Oh, but it didn't give you the E though. Let's try it again. 2 separate buttons, not at the same time. Second and then EE. There you go. Yeah, there you go.
You do second key?
Yeah, so do second EE. There you go. And then do negative. Yep, and then 14. And now divided by. And then negative 3. There you go. Did you get it? No? Okay, so let's not use this times 10 to the, let's just use the second EE button. So let's go ahead and clear that out real quick. Do 1.00, and then do second EE, and then do the negative, and then, oh, not that negative. Back up, delete. All right, do this negative down here, and then 14, and then divide it by, and then you can do the next number. Okay, and then the exponent, and then equals. Okay, so now this is the answer that you see up there, but the one that we're doing here, you forgot, you didn't put this number in. But yeah, so that answer will be when you put that answer in. So this one was for the one you have up on the board. All right. Anybody else have questions? Okay, let's continue on. So one of the things that we want to understand is the difference between strong acids and bases versus weak acids and bases, right? Now, we learned that before. We learned that the strong acids and bases do what? They completely ionize or dissociate, right? They're going to completely come apart. The weak ones don't. But what this means for us is that if we have a strong acid or a strong base, that if we are given the concentration of the solution of the actual acid, then we can translate that into the concentration of the hydronium ions, if it's an acid, or of the hydroxide ions if it's a base. Okay, so if it's a strong acid, the concentration of the acid is the concentration of the hydronium ions. If it's a base, and it's a strong base, the concentration of that strong base is equal to the concentration of the hydroxide ions. Okay, and so why that's helpful to us is because on a test, sometimes they're going to give you the concentration of the solution of the acid, not the concentration of the hydronium ions. But you can just say, oh, well, since it's a strong base, or since it's a strong acid, you know that the concentration of the hydronium and or hydroxide ions are going to be equal. Okay, and the reason again for that is, remember, if we have the dissociation of a strong acid, it completely dissociates. It's a 1-to-1 ratio. For every one of those HNO3s, you have an H, right? It's a 1-to-1 ratio there. And so that's why you can say that the concentration of the HNO3 is equal to the concentration of the hydronium ions. And so in this case, you see that this 1.0 times 10 to the negative fourth, we can go ahead and plug it into our hydronium ion concentration so that we can get our answer. We get our K value and we have our formula, boom, boom, and then we plug it in to get our answer to the concentration of hydroxides. Because we know the concentration of the solution of the acid, since it's a strong acid, we can use that to make our hydronium ion concentration, and then we can use that to solve for hydroxide ion concentration. Because we still know our K value, and we plug that K value of 1 times 10 to the negative 14th into that space. Questions on that? Strong acid means what? I'm going to call on somebody. If I have a strong acid, it means astatine. And that I'm going to be able to say what with regard to my concentrations of my solution? Good. Concentration of my strong acid is equal to the concentration of my H3O+. Okay, good job. All right, so then that lets us solve problems like this. Okay, So you can see here, it says determine the hydronium and hydroxide ion concentration of the 3.0 times 10 to the negative second molar solution of NaOH. What can you tell me about NaOH? It's strong, right? So this is a strong base. All of my hydroxides that are soluble are going to be strong. And so I know this is going to be completely separating apart, right? Completely ionizing or separating. In this case, it's dissociating because it's an ionic compound. And so I can go ahead and calculate now the hydronium and hydroxide concentrations using this information. See if you can do it.
So with NaOH, strong base.
Okay, so basically, if we think about the formula here, for every NaOH I have, it's going to break into one Na positive and one OH negative. So if I have two of these, I'd have two of these. If I had 1,115 of these, I'd have 1,115 of these. Because I have one OH here and one OH there, however, how many I have of these is how many I'm going to have of those. How does that help us? Because they're telling us the concentration of the NaOH, which means I also can figure out
No, that sucks.
Thank you.
Good question.
That sucks.
What'd you get? Just like you're looking at the dissociation.
I really did just don't understand. So that one.
I'm confused at the bottom where it says how the result be different. Because CA has a charge of 2+, so would that affect anything?
Well, the big hint here
OH is 1 minus.
is that word there.
Soluble.
Yeah. So you'd have to look at your solubility table. They're hinting that you should look at your solubility table for
I
that
don't
one.
understand what I was supposed to do at the 3.0.
So that one now becomes your concentration of hydroxide.
So then I have to like set an equation.
Right.
Like the KW.
Mm-hmm.
Without variance.
KW.
Is variance soluble? Would it?
This is your hours.
Mhm.
So you know how you put like two,
Mm-hmm.
stuff like that. Would it be equal? Like the concentrations?
For hydroxide, it is.
It is, but then for H,
So that's what we're solving for, right?
yeah.
And so for hydroxide, we can just say, oh, well, it's 3.0 times
So
10 to
it's-
the negative second,
Oh, okay.
right? And now we have our KW.
Okay, so the OH is heavy. It's not 3.0 times 10.
That'd be 3.33. So you just plug it in as the value it is. It wouldn't be 1 times 10 to the negative 7th. You just keep the value of the
Just like it is here. Because the concentration of hydroxide is the same as the concentration of sodium hydroxide. Just like those were the same.
I thought before it was a 1.0 times 10 to the negative 7.
Well, that's where we're going to get here. So we have to rearrange this formula to solve for hydronium. So now our hydronium ion concentration is equal to our Kw divided by our hydroxide ion concentration, right?
Would the hydroxide be 3.0 times 10 to the negative 2?
Mm-hmm.
Okay.
Wait, isn't calcium soluble in hydroxide?
Is calcium hydroxide soluble? That's the question.
Oh yeah.
Would it be 3.3 for the sig figs because you have the 0.0?
So we just have 2 sig figs, right?
So it'd be 3.3.
All right. So that's your work, right? You would write out your givens, hydronium ion concentration, hydroxide ion concentration, and Kw. The reason you know your hydroxide ion concentration is because your 3.0 times 10 to the negative second molar of sodium hydroxide is going to give you 1 hydroxide for every sodium hydroxide, so they have to be the same. That's why we can say that we know this one right here, okay? And then we write out our formula, rearrange to solve for hydronium, plug in our values, and for our answer, rubidium, we're going to get what? Okay, 3.3 times 10 to the negative 13th. Okay, did you guys get that? Raise your hand if you did. Molar? Yep, good job. All right, now the next one is a little bit tricky because it says, how would the result be different if the base had been calcium hydroxide? And it says, is it soluble? Raise your hand if you looked this one up. You looked it up on the solubility chart. And you found that the solubility chart said what? Insoluble. Okay, yeah. So if you look at hydroxide and you don't find calcium up here, that means any other cation, it's low solubility. It's going to be insoluble, which means that this happens for sodium hydroxide, but for calcium hydroxide, does that split up? Does it dissociate? No, okay? There's nothing that happens. It's insoluble, okay? Now, does it happen at a very small amount? Yes, but it's not considered a strong base at this point. It would be considered a weak base. And so remember, for weak bases, we would have to get a different answer. For weak bases, you have to actually do experiments to figure out whether or not, you know, the K value is such and such or whatever it is. And so for the strong base, we can just make this assumption, but we cannot make that assumption for weak bases. Okay. Yes, it's going to dissociate a small amount. We'll have a K value for it, but it's not going to give us a 1-to-1. And so, yes, my result would very much be different. If it had been calcium hydroxide, I would not have nearly as much hydroxide in there. And if I didn't have as much hydroxide in there, that means I'd have a lot more hydronium. Okay. Now, what about if I had barium hydroxide? And you'll notice that it gives us a hint of second ionization step. You guys remember what we talked about with first ionization and second ionization of acids? How the H2SO4 might break apart once, but then when it breaks apart the second time, it doesn't fully break apart like it did the first time. The second ionization step is a weak step. So I might have a strong acid H2SO4, it's strong and it completely dissociates, but the HSO4 minus doesn't. It's a weak acid. Same thing here. My barium hydroxide, my first dissociation might be strong, but my second dissociation is going to be weak. So I'm not going to get as many hydroxides. I'm not going to get double. I'm not going to get 6 times 10 to the negative second, where I get 2 hydroxides for every time. But I am going to get some. Maybe it'll be 4 times 10 to the negative second. But because it's weak, I don't know. I'd have to do an experiment. And so I'm going to get a different answer, but I don't know exactly what it's going to be. But the value in my final answer would be, you know, not 3.3. What did you get? You had 3.3 times 10 to the negative 13th. It's probably going to be a little bit different than that, right? Because you're going to have a slightly bigger denominator. Maybe my denominator is going to be a 4 times 10 to the negative second. So that means my hydronium ion is going to be a little bit smaller. So I'm going to get a slightly less amount of hydronium ions if I have a greater concentration of hydroxide ions. Okay? Does that make sense? Raise your hand if you understand what I'm talking about. Okay, question.
How do you know if the second ionization is complete? You said if it breaks apart and
Yeah.
like completely ionizes.
Great question. I don't know of any second ionizations that are complete. So basically, you're just going to assume that no second ionizations would be complete. Even if you had a strong base in the first or a strong acid in the first, you will not have a strong in the second. So it'll be a weak acid or a weak base. Good question. Okay. Any other questions?
So wait, essentially, if it has multiple hydroxides or
Mhm.
multiple like hydrogen ions that can give away, you would automatically just consider it like indeterminate.
Yes, you would need experimental values to determine if it had multiple ones to give away. Yep, absolutely. All right, good question. Where is fluorovium hiding? There you are. Okay, so let's look at how this ties into pH. Okay, so you guys were, for the most part, I think most of you are pretty familiar with how logarithms work. Some of us might need a little bit of a review. Just to kind of give you a basics here, we know that pH is from the French, which basically was meaning the power of hydrogen or the potential of hydrogen. Okay. And so we have a formula for it. It is the negative log of the hydronium ion concentration. So now we are going to start seeing how these values, these K values that we've been learning about, are actually connected to our pHs. So we learned that hydronium ion concentration in a neutral solution is 1 times 10 to the negative 7th molar, right? That was the concentration of a hydronium ion concentration in a neutral solution of water, okay, where it's just pure water. And so if we take the negative log of that value, then what's going to happen is that's going to turn into the number 7. So that exponent there is going to basically be the source of your pH. So all this time we've been learning about pHs, we didn't really realize that this was a mathematical connection. It's kind of cool, okay? We have a mathematical connection to that number that we associate with values of our pH and the actual concentration. So for those of you that are trying to remember what logs are, all right, remember the logs are basically just going to be the power to which 10 is raised, okay? So in the case of 10 to the negative 7th, a log would be negative 7. But you'll notice that the value that we had on that formula was a negative log. So log of 10 to the third would be 3. What would log of 1,000 be? Still 3, right? Because 10 to the third is 1,000, right? And so we're still going to end up having the same answer. You just got to take whatever number you have and turn it into a 10 to the something number, and then that something is going to be what you bring out of your log. So if you have a decimal for your pH, it's because it's 10 to the 3.5 or whatever it is, okay? All right, so what is the log of 100? 2, right? Because that's 10 to the second. And so we pull that 2 out of there, and we're going to get our answer of 2 for our log. Okay, so we kind of understand how logs work again. So if we think about that pH of the neutral solution, and we just talked about that with you guys, we said it was 10 to the negative 7th, so our pH is going to be a negative log of 10 to the negative 7th, so that's negative 7, which of course is 7. So let's choose some random acidic solution, okay? Oh, so because you are, which part are you getting stuck on, this part up here or down here?
How'd you get 7? No, how'd you get
This one here?
Yeah.
That one is from a neutral solution of water. And so what we did, this goes back to what we showed you a few slides back where we were like, what is water's concentration of hydronium ions? And we found out that when you did experiments with it through the amount of electricity, you found that 10 to the negative 7th of these water molecules were swapping back and forth and becoming hydroniums and hydroxides. So that original 7 came from an experiment. We know that water has, at 25 degrees Celsius, has 10 to the negative 7th of them swapping back and forth at any point and being hydroniums and hydroxides. Good question. Okay. You are Tennessee. All right. So then we go to our acidic solution. And our acidic solution, let's just choose any random acidic solution. In this case, we're going to go ahead and choose something that is 10 to the negative 5. Okay, that's a higher concentration of hydroniums. If hydroniums are more than hydroxides, it's acidic, right? So we choose a hydronium ion concentration, and that is going to give us a pH of 5, right? So we can see that that 5 is connected. If we choose any sort of random basic solution, let's say we're going to choose something with 10 to the negative 9th, then that pH is going to be 9. Okay, you see how easy it is? So there's a mathematical connection. That's where we get our pHs. Now, the wild thing is, we learn about this pH scale. We learn from 0 to 14, and we can see like our stomachs are looking at pH, which is, 1 or 2. Our battery acids are 0, drain cleaner 14. We can see all these values. But what we don't learn about in high school, and I didn't learn about until I became a teacher, didn't even learn this in college, is that the pH scale goes beyond this. Now, it makes sense that it would, and I was always thinking I feel like it should go beyond that, but none of my textbooks ever said that. And so I just said, oh, I guess it must not. No, maybe, I don't know. Anyway, it does, okay? In fact, the biggest pH, okay, if you think about it, that we have is going to be something in the negatives. Because look, this is 1 molar hydrochloric acid down here, and that's a pH of 0. Well, we've got 12 molar hydrochloric acid in the chemical closet. That's a higher concentration, which means my pH has got to be in the negatives. In fact, the most negative pH that we have, I think, is like a negative 33. Okay? So you get something that's really, really, really concentrated, and you can get some very low pHs. So no, that's a good question. Acids are kind of weird. Like, have you ever thought about like why acids can be stored in plastic containers and they don't burn through those, or glass containers? Like, they'll eat metal, but they won't eat plastic, right? And so some acids do certain things with certain materials compared to other ones. So you wouldn't want to put sulfuric acid in a plastic container. You'd put it in a glass container. But so yeah, it doesn't, having a really high or low pH doesn't necessarily mean it's going to have more toxicity to certain materials. It depends upon the material and the reaction. All right, so you can see on this one that we have a huge range of values that we are dealing with here, right? This huge range that we are going to be dealing with because it's a logarithmic scale. Every 1 pH you go up is a value of 10 times more acidic or basic, right? Because you've got 10 times the amount of material that's in there, 10 times the amount of hydronium or hydroxide concentration. And so you're going to have a big jump in those values, okay? So you'll notice here that we have our pH formula, but look, we also have a pOH formula. And you'll notice it tells us we need to memorize both of these. The pH is the negative log of hydronium, but the pOH is the negative log of the hydroxide. Now, the other thing that's kind of interesting to pay attention to is that if you add the pH and the pOH together, you get 14. Just like when you add the hydronium and hydroxide concentrations together, or multiply, you're going to get 1 times 10 to the negative 14th. If you add the actual pHs and pOHs together, you get the actual number 14. Okay? So we'll go ahead and stop there. Tomorrow we'll finish up on 15.1. We haven't quite finished this lecture yet, but good job paying attention and working hard today, and we'll finish up tomorrow. A bit of review. You guys already know this formula here, right? So that was your pH formula, minus log, or the negative log of the hydronium ion concentration. And then we're introducing this next one. You'll notice it's very similar. It's the pOH is equal to the negative log of the hydroxide ion concentration. Okay, so you'll want to know that equation as well. So if you have your hydroxide concentration, you can figure out what your pOH is. These kind of just tie into each other because if we add a pH and a pOH, we get to 14. Now, this is going to be true of all of the values that we use that are between 0 and 14, right? We talked about how some values could be negative if you have more concentrated acids, and so it's not going to be something that we will do with those. But for everything that is in that 0 to 14 range, you add those together, and they're going to give you 14. Now, just a little reminder, we talked about this just a second ago or a bit ago when we talked about yesterday's lecture. We said that 1 molar hydrochloric acid solution, this is HCl right here, that has a pH of 0. Okay, and so anything below that, anything that's more concentrated than 1 molar would then start going into that negative value. And anything that's more concentrated than a 1 molar solution of sodium hydroxide would now start going above 14. Okay, so we typically do not have values that we deal with in those areas, but those things do exist. Okay, so now let's talk about how we can move from one pH to another and how small of a change it takes. So if we're talking about just 1 liter of water, we know that our pH, if it's pure water, is going to be 7 because we have a hydronium ion concentration of 1 times 10 to the negative 7th. Remember that there's an equal amount of hydronium and hydroxide ions. They're just exchanging back and forth between each other. And then if we just change it just a little bit, all right, maybe this is adding a small amount, depending upon the concentration of your acid that you start with, you might be adding a very small amount of hydrochloric acid to your solution, and suddenly your pH goes all the way down to 2. Okay, you're at 1 times 10 to the negative 2nd of these, moles of these HCl molecules that are now ionizing in your water. And so it doesn't take very much at all, 0.01 moles, and suddenly you are in a situation where you are going to have a pH of 2, drops very quickly. And then you add just a little bit more, and now you're at 0.1 moles, and suddenly you are at a pH of 1 because you're at 1 times 10 to the negative 1st molar hydronium ion concentration. Okay, you can see that for salt, if I'm adding salt in there, I'm not going to have my pH any different than I did with my water, because salt does not create hydronium ions. It does not create hydroxide ions in solution, right? And so you're going to end up with the same pH as you did with regular pure water because you're not making any more hydronium or hydroxide ion concentrations, okay? But if you add a little bit of hydroxide, suddenly your pH is 12. A little bit more hydroxide, suddenly your pH is 13. And what we just saw in that last one, if we make this a 1.0 mole, all right, which of course we're just adding and moving that decimal point over 1 time each time, you're going to end up with a pH of 14. Okay, 10 molar concentration, then you can imagine that that's going to pop up again, a factor of 10 each time. Okay, so this is kind of giving you an idea of how small a change you are making in terms of the concentration of the solution, and yet how big a change in pH you can get. Okay, if you think of a dilution that you would create, if I have a 1 molar solution of sodium hydroxide, and I want to get a mole of sodium hydroxide, then I can do the calculations. You guys remember we learned how to do an equation that told us how to do dilutions. The molarity or the concentration of one times the volume of one is equal to the concentration or the molarity of the other times the volume of the second one. And so you can make pretty easy calculations with your concentrations, and you're going to be able to see these things changing pretty quickly. Okay, so it doesn't take much to change these concentrations. Now, we do have the ability to take a pH and figure out a concentration from the pH, right? Before we took a concentration, right, our hydronium ion concentration, and we applied a negative log to it in order to figure out the pH. But what if we started with the pH and we wanted to figure out the concentration? Well, we could do that by doing what we're going to call the anti-log, right? So if we think about the expression log of x is equal to y, that means that y is the exponent needed on a base of 10 in order to equal x. In other words, log of 3 is equal to 0.477 means that if I take 10 to the 0.477 power, I'm going to get a 3. So When we did the pH one, remember we took our hydronium ion concentration. We were able to figure out our pH value by taking the log of it. Now we can actually go the other direction, and we can take the pH and figure out a hydronium ion concentration. So let me show you how that works. Okay, so we have got our formula here that you're also going to want to learn. The hydronium ion concentration is equal to 10 to the negative pH. So this is going to let us plug in that pH value into a formula and figure out our hydronium ion concentration. So if I have a pH of 1.52, I can just take that and say, hey, that is going to be my exponent on the 10. And I put it into my calculator, 10 to the negative 1.52 power, and I'm going to get an answer. That answer is going to be my concentration of my hydronium ions. Okay. Now, when we do sig figs on logs, they're only the digits after the decimal. So in this case, we're only paying attention to like the 0.52. We have 2 digits, and so that's all we're paying attention to. I'm not going to pay attention to your sig figs on these types of problems. Okay, so while that's the rule for this, I'm not going to make you guys pay attention to that particular part of this. So you should be able to now, you take the same formula and find the hydronium ion concentration in a fruit juice that has a pH of 3.3. So let's see if you can plug this into your calculators and figure out what this concentration is going to be. Yeah, I'm not going to, the longer version of it versus the scientific notation version. Is that true? Yeah, I'll take it with the scientific notation or not.
I got. Yeah. Wait, why does he put in? Is that just what I have to do?
Would you rather like inside
You put your shit back on?
I'm okay with either way. Ones that can kind of get long, you definitely want to do it in scientific notation.
Yeah, 1 and then someday. Someday. Lay down. Here you go.
All right, let's see how we did this one. Polonium. Where are we at? Polonium. That's you. What do we got?
So I got 5.01 times 10 to the 4th.
Because you did what?
Because I put 10. I did second log, and it has 10x in the variable, and then I did minus 3.3 on the x, and it gave me this answer.
Time out.
Okay.
I got that, but I got negative exponent of 4. I care. It might not mean much to you, but this means a
I was
lot.
talking about I'm not going to get points for answering that question because I'm not boring.
He said about me.
So you got, say the answer one more time. We did 10 to the negative 3.3, and you got?
5.01 times 10 to the 4th.
Okay. 10 to the negative 4th or 10 to the 4th? All right. And that's your concentration. So what are my units? Molar, right? Okay, so again, if you had the 5.01, the sig figs, I'm not paying attention to the sig figs. But if you had 5.0, that's fine. I'm just saying that, you know, typically they're only paying attention to the numbers that come after the decimal point. So there you go for your answer. That's how you do these. Okay. Now we can take this and we can extrapolate it now into a giant box of information. I want to copy this down if you like it, but I want to show you that you can go from one type of a value to another type of a value pretty easily. So for instance, on that last one, we had a 3.3 as our pH. Now, if I asked you to tell me the hydroxide ion concentration of a solution of a material, that fruit juice, that has a pH of 3.3, you should be able to tell me the hydroxide ion concentration of something that has a pH of 3.3. Now, you can do it two ways. You could go along this path, which is what we just started to do, right? We did the anti-log, and we found out that this was a 5 times 10 to the negative fourth. And then we could now go down this path, and we could take that number there and plug it into this, and then, you know, do a solution to figure that out. Okay, I guess not that one, this one. And then we would take that one, and then that would give us our hydroxide. Or we could do it the other direction. We could say, hey, well, pH of 3.3 would actually be a pOH of 10.7. So now let me take the value of 10 to the negative 10.7 and get my answer over here as well, right? So there's a few ways that you could come up with an answer of the hydroxide ion concentration if you were given the pH. So it depends upon which route you want to go, but you could go over the top and down, or you could go down and then over the bottom. And so this is kind of a nice little table that will help you to relate each of the different ways that we can express our concentrations and our pH and pOH values. Does anybody have any questions on those? Okay, I'll give you another minute to finish writing that down for those of you guys that are doing that. Thank you. Okay, and you got all those beakers all finished off? So you're going to take these numbers here, and you're going to write them down for each of the students that we have, okay? So you can take that, and then they're not going to be in the same classes that they are on here, but I want them to put them in here. So you're going to have to sort them a little bit and make sure they get into the right places. So you have to sort the period first into these ones, or you can just look for them. You can be like, oh, well, I didn't see them in fourth period. Let me see if I find them in this period. Mostly the same, but there's going to be a few kids that are different places. Okay. All right, everybody got that written down?
Yes, sir.
All right.
Are you good to 3?
We are just about there. Okay, so we are going to start next on our 15.2, but first we're going to grade before we do